Good afternoon, everyone. And despite your busy schedule, please thank you very much for coming to annual symposium on ITER BA activities. I am your moderator, and my name is Moe Akimitsu of National Institute for Quantum Science and Technology. And at QSD NECA Fusion, I develop plasma Thomson diffusion measurement system to measure plasma electron temperature and density. And also, I study plasma-related safety. Thank you very much for your time. And first of all, on behalf of the organizer, President of QST, Shigeo Koyasu will address us. Thank you. I am Shigeo Koyasu, President of QST, and I would like to express my sincere appreciation for coming to this symposium despite your busy schedules. And at QST, we pursue a broad spectrum research and development under the banner of quantum technologies ranging from energy to medical applications. So we cover quite a wide range, and fusion energy is something that we have been engaged for so many years. At ITER BA Symposium has since last fiscal year been organized under auspices of QST as a part of the progressive reorganization of the Fusion Energy Forum. And as we did last year at this symposium, we are pleased to hold the event concurrently with the Industry Exhibition and the Industry Youth Dialogue 2025, both organized by Fusion Energy Industry Council. And I would like to express my sincere appreciation for the Council for its generous cooperation. With regard to fusion energy, the government's Integrated Innovation Strategy 2024 set forth the goal of aiming for the early realization of fusion energy, including development of a national roadmap toward achieving electricity generation demonstration in the 2030s ahead of the rest of the world. In line with this direction, and QST is accelerating its effort by developing full-scale test facilities and equipment designed also to support startups and other emerging players in order to advance the necessary technologies. And through these initiatives, will continue to contribute both to the realization of a sustainable future of society and development of our local communities. I'd like to briefly talk about what we are doing at QST. And last year, we held the 40th anniversary ceremony of the Naga Fusion Institute, where we declared our commitment to establishing it as an international hub for fusion energy. In this context, 2 U.S. national laboratories will be joining the JT60SA project. And looking ahead of the plasma heating experiment scheduled to be 2026, for the first time, we'll be using mixture of expert AI to control plasma shape and position. And we have also installed the world's highest power neutral beam injection system, along with an 8-meter diameter coil capable of rapidly controlling plasma configuration. In the ITER project, we have completed the full-scale outer vertical target of the diverter, and we have developed a gyroton capable of generating high-power microwaves suitable for application in demo-class reactors. These efforts represent steady progress and technologies developed through the ITER project, such as monoblock tungsten components, copper alloy cooling pipes, and gyrotons, have been highly evaluated, leading to new orders from Europe and ITER organization, thereby contributing significantly to the advancement of Japanese industry. At the Rokkasho Fusion Energy Research Center, we have proposed to the government an accelerated plan for the demo reactor program in line with the revised fusion energy innovation strategy, which calls for achieving electricity generation demonstration in the 2030s ahead of the world. And to this end, we are currently advancing the conceptual design of a ITER scale demo reactor with the aim of completing it by the end of this fiscal year. And regarding the ITER program, we will also receive a keynote report via live broadcast from Dr. Brabowski, Director General of ITER organization, on the current status. And we have a time to exchange opinions with the Director General, and we also have also organize a live broadcast discussion between ITER organization and staff and young participants. And I sincerely hope that today's ITER BA annual symposium will prove meaningful for Japan's demo reactor program and for our broader efforts toward realizing fusion energy. Again, thank you very much for your participation today. President Koyasu, thank you very much. Next speaker is, despite your busy schedule, I would like to ask the guest to give us a few words, and I would like to invite Mr. Eisuke Mori, Chairman of the Liberal Democratic Party's Parliamentary League for the Promotion of Fusion Energy. Thank you for your introduction. I am Eisuke Mori, Chairman of the Liberal Democratic Party's Parliamentary League for the Promotion of Fusion Energy. And it is a great honor for me to take part once again in this annual symposium where all those involved in the ITER BA projects gather together. And also, I am so delighted to be invited to this occasion. Again, thank you very much for having me. And the Fusion Energy Innovation Strategy, originally formulated in 2023 under the leadership of the Minister of Science and Technology, Sanae Takaichi, was revised June last year. The updated strategy clearly states Japan's commitment to achieving the early realization and industrialization of fusion energy, including demonstrating electricity generation in the 2030s. And to reach these goals, it is essential that we all work together, industry and academia. And today, this parliament, I'm a chairman, and about 40 years, we have been working on this theme. And I joined the league about 25 years ago. And fusion energy, I have been playing a role to promote fusion energy. And during that time, I recall that there was an intense competition that unfolded between Japan and Europe when the site for ITER was being selected. As a result, it was decided that France was selected. Instead, Japan would carry out a broad range of activities under the broader approach in cooperation with Europe. And as a part of that broad cooperation, there was some twists and turns, but under Director General Brabowski and Mr. Kamada, and the leadership of those two leaders, with so many parties collaborating, I understand that this project is making a steady progress, and I am happy to hear that. And for important technologies and equipment, Japan is participating and contributing. I cannot be any prouder. And the broader approach activities hosted by Japan are progressing smoothly in Rokkasho Village in Aomori Prefecture and Ibaraki Prefecture, supported by strong local engagement. and international cooperation between Japan and Europe. And I understand that the project or those activities are yielding very significant results. In the ITER program and through broad approach, knowledge and experiences are produced and they are being utilized in Japan. And Japan is acquiring core technologies. And for fusion, it is extremely important for Japan to maintain its position at LDP. With the LDP party, a project team has been established under Policy Research Council, and policy recommendations were issued in May of the year before last year game. And as a parliamentary league, we will continue to work closely with the government and provide our full support going forward. In conclusion, I would like to express my sincere appreciation to all those who have worked so hard to get this meeting possible. And I hope that this will be a catalyst for us to leap forward into the future. And everyone who participated and contributed to this occasion, I would like to say thank you. Thank you for your attention.
Thank you very much, Mr. Mori. Next, I'd like to welcome the Senior Deputy Minister of Education, Culture, Sports, and Science and Technology, Mr. Yasuyoshi Kakita. I am Kakita, Senior Deputy Minister of Education, Culture, Sports, Science and Technology. On opening of the annual symposium on the ITER BA activities, I would like to give a few words. First, I'd like to express my sincere respect and gratitude to the Chairperson of Liberal Democratic Party's League of Diet Members for Fusion Energy Promotion, Mr. S.K. Mori, the Diet members, all the representatives from the industry and academia, and the relevant municipality from Ibaraki and Aomori, and also the members of the National Institute for Quantum Science and Technology, and all the participants present today for the dedicated efforts in making this meeting possible. Fusion energy is a next-generation energy source that can solve energy and global environmental issues simultaneously. To this end, major countries are formulating national strategy and establishing startups. And consequently, international competition is now accelerating. In our country, under the leadership of Prime Minister Takaichi, in November last year, the Japan Growth Strategy Council was held. And it outlined as a policy to promote both investment and public-private partnership in fusion energy as one of the 70 strategic fields. And based on these initiatives, it is important that cutting-edge achievements of the ITER project and BA activities to be reported in this meeting need to be steadily permeated in Japan in collaboration with the Japan Fusion Energy Industry Council. Last year, I myself had an opportunity to visit ITER construction site. Following the delivery of the toroidal fuel coils, which completed last year and also the ITER project is now progressing with the delivery of gyrotrons and diverters. These components represent the concentrated technological capabilities of Japan, including the small and medium-sized companies, demonstrating the presence of Japanese industry to the world. I also understand that the number of Japanese staff members working at the ITER organization is increasing. This is a very positive trend, not only from the perspective of contributing to the ITER project, but also from the perspective of developing human resources in our country. We will continue to strengthen our support for human resource development utilizing this project. In the VA activities, the world's largest Tokamak device, the JT60SA, built in Naga City, Ibaraki Prefecture, based on the cooperation between Japanese and European governments, will see resume full-scale operation after going through upgrading of 2 years. Additionally, in Rokkasho, a village in Aomori Prefecture, the new supercomputer Sosei has commenced operation. I am expecting that initiatives such as computational simulation research will steadily be promoted. The Ministry of Education, Culture, Sports, and Science and Technology also believes that ITER project and VA activities play a significant role in acquiring the core technologies necessary for fusion energy, and we will steadily promote them. At the same time, we would like to support the basic research. At the same time, supporting fundamental research, we will take new initiatives such as the DONES project developed in Europe. I would like to ask for your continued support in our efforts, and I sincerely hope that today's symposium and the fusion energy industry Japan will be successfully proceed in order to realize the future fusion energy. Thank you very much. Thank you very much, Mr. Kakita. Next, I would like to ask the Vice Chair of Keidaren Japan Business Operation, Chair of Committee on Mutsu Ogawara Development, and Chairman of the Board of Mitsubishi Heavy Industry, Mr. Seiji Izumisawa, to give a few words. Thank you for your introduction. I am the Vice Chairman of Keidaren and Chairman of the Mutsu Ogawara Development Promotion, and I am from Mitsubishi Heavy Industries. I am responsible for promoting the development of Mutsu Ogawara Development District, where QSD Rokkasho Institute for Fusion Energy is located. I'd like to extend my heartfelt congratulations on this year's symposium on ITER VA activities. On behalf of the business community, let me give a few words. The intensified U.S.-China confrontation and Russia's invasion of Ukraine have significantly destabilized the international orders, creating uncertainties and the instability of energy supply. On the other hand, against the backdrop of the rapid proliferation of generative AI, power demand is increasing significantly. Under this circumstance, securing affordable and stable electricity while promoting decarbonization has become an extremely important policy issue in strengthening Japan's industrial competitiveness. One of the key to resolving this challenge is utilization of nuclear power. Firstly, the government and operators will continue to steadily work towards restarting existing nuclear power plants with safety and understanding of local communities as the prerequisite. Furthermore, discussions on new constructions and replacement projects are expected to take place. Furthermore, looking ahead toward the future as the ultimate energy source, we must persistently advance technological development and social implementation of fusion energy. Amidst this situation, in the government's 7th Strategic Energy Plan, a policy to maximize the use of nuclear power has been set, as well as a commitment to continuously pursue technological development towards the practical application of future energy. In addition, the government has announced the pioneering power generation demonstrations in the 2030s and plans to strengthen public-private sector R&D capabilities. Moreover, under the Takaichi administration, launched last October, it has been clearly positioned as one of the pillars of national strategy. Such strong backing from the government is most welcomed by the business community. On the other hand, fusion energy is a field requiring extremely advanced and long-term technological development. Therefore, it is essential to avoid grounded R&D, human resource development, and the establishment of an industrial foundation from a mid to long-term perspective instead of a short-lived approach. It is crucial that stakeholders from industry, government, and academia share a common goal and create an environment enabling steady progress towards 2030's power generation demonstration, the first step towards realizing fusion energy and towards social implementation. For the large-scale system, not only the core system, but the peripheral technologies are also important. 2025 has been a year in which Japan demonstrated steady contributions and tangible results, both in the ITER project and BA activities. The toroidal fuel coils for ITER, including those manufactured by Japanese companies, have been integrated with the vacuum vessel sector and started to be installed in the Tokamak pit. Even though this is my personal story, when the first device has been sent from Kobe in the year before last year, I was able to see the device at the ITER site. It was like being reunited with my child. The first prototype of the diverter outer vertical target, which is being developed by Japanese companies, has also been completed. I understand that research is also a progress in MBA activities towards establishing the technological foundation required for fusion demo reactor. At JT60SA, following the initial operation phase, power increase and facility maintenance are being carried out in preparation for the next performance enhancement phase. And to this end, the Japanese companies are playing a central role with the expertise in the construction modification that they have acquired through the years. Going forward, it will be critical for Japan to maximize the utilization of these achievements through close collaboration among industry, government, and academia to build an international competitive supply chain and create a fusion energy, given that it is essential to energy security and sustainable growth. I would like to reiterate once again that realizing fusion energy is a long-term challenge that we have to keep on taking on. I conclude my remarks by expressing my hope that today's symposium will foster a shared understanding among all the stakeholders and serve as an opportunity for further promote steady and continuous efforts. Thank you very much.
Thank you very much, Mr. Izumisawa. Next, we'll have Mr. Kitano, Chair of the Sustainable Energy Committee of the Japan Association of Corporate Executives and President of JFE Holding. Hello, everyone. Thank you very much for your kind introduction. I am Kitano, the Chair of the Sustainable Energy Committee of the Japan Association of Corporate Executives. I'd like to congratulate all of you on the opening of the 2025 Annual Symposium on the ITER project and BA activities. It is also a great honor for me to have this opportunity to speak to you. First, I'd like to express my deepest respect and gratitude to all those involved in advancing the ITER project. Fusion energy holds the key to unlocking the future of sustainable energy. Expectations for its social implementation continue to grow in the industry every year. Recent energy trend calls for striking a balance between affordable, stable energy supply and environmental protection. Particularly as global warming and climate change become increasingly serious, securing clean and sustainable energy has become our largest challenge. From this perspective, fusion energy is expected to provide an innovative solution to future energy supply. Since Japan is an energy resource importing nation, fusion energy development is a major theme that we should address for the sake of future generations. Last year, the Japanese government included fusion energy among the 17 priority investment areas in the national growth strategy. It demonstrates Japan's strong interest in the technology and its high value. Furthermore, the establishment of Fusion Energy Office in METI's Agency for Natural Resource and Energy last November is indicative of the Japanese government's strong commitment to the development and commercialization of fusion energy. I believe this strong momentum will attract talented students so that we can nurture young talents who will contribute to the advancement of fusion research. The Japan Association of Corporate Executives published an opinion statement about nuclear energy last fiscal year. We also compiled opinions of the draft 7th Basic Energy Plan last year. Throughout these interactions, I sense that the growing expectation and the momentum surrounding fusion energy. The ITER project is viewed with great anticipation as part of an international effort to commercialize fusion energy. It is also a symbol of international collaboration, bringing together different nations and cultures to work toward a common goal. We strongly believe that this spirit of international cooperation will accelerate technological development towards achieving fusion energy, while also paving a new path for solving global challenges. In the Fusion Energy Innovation Strategy, revised last year by the Cabinet Office, a roadmap aiming at the world's first fusion power generation demonstration in the 2030s will be formulated. That is, a necessary fusion industry ecosystem will be established. A step-by-step advance in technologies demonstrates solid progress towards the project's success. That's heartening for all of us. The practical application of fusion is expected to reduce energy costs and create new industry and jobs. This will spread positive impacts across the entire economy, laying the foundation for sustainable growth. Fusion energy significantly reduces greenhouse gas emissions and helps solve issues, making a major contribution to environmental protection. Our mission and responsibility for the future generations are to ensure fusion energy as a clean and sustainable source of energy, contributing to solve environmental challenges. In closing, I hope this symposium will further advance collaboration in research and development across industries and continue to develop as a platform for realizing future energy. Thank you very much for your kind attention. Thank you very much, Mr. Kitano. Besides all the guests that we have spoken, we have some. We would like to introduce our distinguished guests. From the left, on the far left, Upper House Member of Parliament Diet, Mr. Kira Shuji. Thank you. Upper House Member of Parliament, Morimoto Shinji. Thank you. Upper House Member of Parliament, Mr. Kamatsu Ken. Thank you. Upper House Member of Parliament, Mr. Goto Shota. Upper House Member of Parliament, Mr. Katsume Yasushi. His secretary is here on his behalf. Thank you. Naka City Mayor, Masaki Hikaru. Thank you. There are many cable messages. I'd like to introduce only the names of the senders. Lower House Member of Parliament, Mr. Tanahashi Yasufumi, Mr. Aoyama Yamato, Lower House Member of Parliament, also Lower House Member of Parliament, Ms. Okada Hanako. Thank you very much.
And through live broadcasting, we would like to invite Dr. Barabaski, Director General, to update us on the construction. And the coordinator is from QSD Naga Institute. Nakahira Masataka or Masataka Nakahira will be moderating this section. Thank you. Thank you for your introduction, and I am Nakahira, and thank you very much for your attention. And after 15 minutes of his presentation, we'll have 15 minutes Q&A, but with conscious of time, we have selected those who will ask questions. But you will only have 1 minute for question and answer, so please limit your question to one per person. And Dr. Barabaski, since 1992, he's been engaged in ITER project, and since 2024, in 2024 he was appointed to be Director General. And please, over to you.
Thank you so much. Thank you so much, Nakahira-san, and thank you all for letting me speak at your venue. I'm very sorry that I cannot be there in person, and but nevertheless, I would be with pleasure give my brief introduction on the status of ITER and a bit of a perspective. So I don't see my slides at this point in time. I am told that they will be put forward by you. Are the slides being shown? Okay, thank you. So please move directly to the next slide. As you probably know, we started our work, say, on reforming the project about 3 years ago. This was in the end of 2022. And at that point in time, we had a number of problems that had to be solved. I don't see my next slide. Please move to slide number 2. Move to the next slide, please. Yes. So we had to go through a major restructuring of the organization to become more efficient. We had some issues with the regulator in France who had lost a bit of trust on us. We had to restructure a number of assembly contracts, repair components that were, had some issues of quality, and develop a new baseline. Now, we cannot but admit that the performance of ITER over the years was not exactly perfect. The schedule performance index was normally between 50 to 60%, meaning that about half, on a little bit more than half of the work planned was achieved. But I'm glad to tell you that year 2024 and 2025, we had a schedule performance index which was in excess of 100%. So 103%, which is pretty good, almost perfect for a project, I would say, with a cost performance index of 115%, which means that the cost was less than baselined on the execution of the work, and essentially no contingency had to be used during this period of time. Please, next slide. So this slide shows in number how the project has moved on. And you see that in 2024 and 2025, sorry, the date is missing there, there was a large increase on the execution rate. And we moved from about 60% execution rate to 80% in 23 and 100% in 24 and 25. But also the amount of work, not only the execution rate was increased, the amount of work was increased dramatically. In 2025, we have executed 84% more work on, say, capital growth assembly activities, 84% more than any year prior to 2022. Next slide, please. So the assembly, machine assembly is progressing very well. We have reset, as I said at the beginning, the contracts of assembly in 2023. So that's why also in 2023, the execution rate was not immediately very large. And we had to remove some of the sector module to be repaired. But now we have back in with 3 sector modules in the pit, where sector module 7 was installed in April, sector module 6 in June, and sector module 5 in November. And we will soon install the sector module, the next sector module next week, actually. So we are very close now to have 4 full sector modules, and we plan to install at least another 4 during the course of 2026. So 40 TF coils from Japan are now in the pit. Next slide, please. We have another a series of other components from Japan, which are, say, well ahead in procurement or in assembly activities. For example, what we use to heat the plasma and the gyrotrons, and also on the divertor. Next slide, please. So now regarding ITER, what are, say, how ITER can be useful as of today, because we want to be still very useful to the community today, even during the assembly phase. Now, first, we have to remember that ITER at the beginning, in particular, was seen more of a place where people would go before retirement with a lot of experienced people. But we want to change that, and we want to create an environment where ITER can also be an environment good to generate the know-how and to generate, say, individuals that can go back to their, say, national program to foster innovation. This is particularly important with the resurgence of the private sector, where that requires a number of young, experienced people. And the experience that can be gained now in ITER during assembly is very valuable. There is no other place in the world where the activities ongoing can be executed. So important to develop, yes, young students, important to develop the companies that will be one day in the supply chain for ITER. And this is something for which ITER has been very strong also in the past years, develop the supply chain. Now, we want to support the private sector, not only by the development of the supply chain, but also to access all the know-how that ITER has developed during the years. And so for that reason, we have since 3 years ago developed a new program to support the very private sector. Next slide, please. I wish now to spend a few words about why ITER is like that, because I realize more and more that when policymakers come to ITER and there is a lot of, say, enthusiasm about the nuclear fusion right now, which is all good, they ask me some interesting questions for which I think an answer should be given. So please, next slide. We cannot say hide that there is such a strong enthusiasm. But at the same time, so in this room there are so many policymakers. It's for me important that they understand well not to have, say, unrealistic expectations, because from my perspective, indeed, there are some unrealistic promises which are being made. And from this perspective, I think we should be conscious about the fact that developing fusion will still require some very important developments still to be done. So there are very important questions that I hear very frequently from visitors. Why ITER is like that? And would it be different? Would we design it now? why does it cost? Why did it cost so much? Because it is no question that ITER has costed a lot of money, and is ITER really enough to develop fusion? So I have tried to present this information also to the council, and I would like to present this to the community, because some of the reason behind ITER may have well been forgotten. Please, next slide. So first, we should remember that ITER was based on three important requirements. The first is to reach the so-called triple product that would lead to what is essentially ignition with conservative assumption. And this conservative assumption were based on the experiment that were done in the 80s and in the 90s. And that led to the requirement of 15 megampere. Then it was decided that ITER had to reach thermal equilibrium, that it could not be a very short pulse, and that the shielding blanket had to be designed so that they could possibly host also the ability to breathe tritium. Now, alongside ITER, that was designed the way it was, with 15 megampere, even in the 90s, if not even in the 80s and the 2000s, there were many proposals of ignition machines that were much more compact. So what was the fundamental difference is that while they could reach possibly a very high triple product, the assumptions were a little bit less conservative. So they didn't have the 15 megampere that ITER had to have. But more importantly, they could absorb very high power fluxes. So they could be very small because they were only running for a very short pulse. So this is the fundamental reason why, or one of the most important reasons why ITER is 6 meters. Next slide, please. Now, a question is what would happen if ITER would be designed today? And I have seen in conference that there are developments in high temperature superconductors that can achieve higher field. And people can say, well, we could make it significantly smaller. Well, I must say that I don't think so. When ITER was designed with niobium-13, and niobium-13 is a type of superconductor that can operate at field much higher than the one that ITER operates to. So the optimization of ITER was based on the fact that higher magnetic field would have meant that the machine would have to operate with power fluxes at the divertor and the first wall that were prohibitive. So even higher than what they are already now. And you have seen a picture of the divertor as it stands, and the divertor now is really the state of the art. A higher power flux could not be absorbed. And that is what sized the magnetic field and sized the surface in order to take the fusion power. And the proof of that is take into account that in the cross-section of the coils, even those built in Japan, only 4% of the cross-section is niobium-13. So if we will have now a superconductor that can carry an infinite current density for a zero cost, we could save only a small percentage in the radial build of the TF coils, and just as much, only a few percent in the size of ITER. And again, as I said before, there were designs in the 90s that could operate at magnetic field, which were much higher. So we could do that with high temperature superconductors as opposed to copper. But nevertheless, the problem is power flux. Power flux is really one of the reasons that drives some of the technology challenges in fusion. Next slide, please. So, and what about the cost? I think this is a very important point for fusion. Fusion remains a very, very expensive technology, and it is a priority that we should set for ourselves to try to simplify and not necessarily reduce the size, but we can say without massively reducing the size, simplify considerably. Now, ITER is more complex maybe than what it could have been. We have added a lot of feature in lieu of the fact that it is an experiment. And there was over the years an escalation of requirements that I think were not, strictly speaking, kept in full check. And we can also say that the complexity in the organization of ITER was massive. So there were many political compromises made. And from my perspective, I should bring this forward. We should not forget about that. Because indeed, one of the knowledge that can be drawn from ITER is not only what can be done effectively, but also what should be avoided. And it is our duty to share openly this to policymakers. ITER is now on a good track, but we should not forget that it went through very difficult times, and we should avoid that other initiatives take, say, and make the same mistakes that unfortunately were made for ITER. And mistakes often happen, but we should not make them twice. Next slide, please. So I come to the fourth very key question: is ITER enough? Is it enough to have an ignition device that reach thermal equilibrium? Well, I must say that I don't think so. I mean, in order to make sure, first of all, that fusion will lead to an energy source where not only more energy gets out than the energy we put in, but more money gets out than the money we put in, we have a number of other technological issues that need to be solved. And ITER will not be enough by itself. So I really feel the duty that I should explain this or highlight at least this to all of you. First, as I said, is the question of cost. We really have to address and we have to find a way to reduce the cost in fusion devices, make them simpler and find technological solution and manufacturing solution which can be made and can be significantly cheaper. Then we have to find a way to deal with the heat flux. In the surface of ITER, we have peaking factors which are about 100. We have regions where the heat flux is 100 times the average. And this is way too much. We have to be able to find, through experimental physics, ways to spread the heat load in a more uniform way. We have to find a way to avoid plasma disruptions. We have to find a way to deal with high energy neutrons. We have to find a way to deal with remote handling for maintenance, so reliability. And finally, we have to find a way to bridge tritium, because even today, we don't have a fully designed tritium breeding blanket that could not even put in a fusion reactor, but not even in ITER, that would sustain the conditions in ITER and produce the needed tritium to operate fusion reliably. So I'm sorry here if I bring forward so many issues, but I really feel the duty to do so, because the last thing I would like is to create disappointment. I think fusion is indeed a very important energy source. It's an energy source that I'm proud to work on, and we have a number of good experiments that we have set in place. I'm proud to say that ITER is now good on track, but we should not forget all the, say, technological and R&D that needs to be set in place. And I say so also because I hear sometimes, once again, that some say, okay, in the next, maybe in the 30s, the next decade, fusion will be on the grid. Well, maybe so. Maybe we can produce some electricity in the grid. But the question is, will it be something which will be produced in massive scale and in an economical way, so that it can really contribute to the economy of our countries? So with this last slide, please move to the next. I would like to thank all the audience to listen to me. Thank you again to all of you for the support that you are giving to Fusion and to the support that you are giving to the ITER project. Excuse myself for not being there directly. And lastly, invite you all to come to visit ITER, which is your project. It is your place to visit. And I will be glad to welcome you directly there and show you how we are doing in the project. Thank you very much.
Thank you, Dr. Barabaski. And I would like to open the floor for questions and answers. To start off, Mr. Akamatsu, a member of House of Councilors.
参議院議員の赤松健でございます。バラバズキさんに2つ質問したいと思います。今トカマークピット内にサブセクターモジュール3つ入って誕生日ケーキでいうと3分の1完成したというところですけど、私現場で行けなくてすごい残念なんですけど、現場で見て相当かっこいいと思うんですけど、機構長の感想をお聞きしたいと思います。もう一個ちょっと機械的な問題で恐縮なんですけど、X の投稿で組み立ての時にすごい今回から精度が上がって、これまで100ミリの誤差しかなかったのが10ミリに なった、改善した。これ特に、設備が変わったわけではないと思うんですけど、どういうふうな工夫があったのかちょっと教えていただければと思います。お願いします。
My name is Akamatsu. I'm a member of House of Councilors, and I have two questions. First one is, in your presentation, you talked about tokamak pit and subsector module. 3 modules have already been installed, and I understand that that's in terms of the progress, that's 1/3 of the way. And unfortunately, I was not able to visit the site, so I was not able to see that with my own eyes. But I'm pretty sure that looks cool with 3 modules being installed. So I would like to get your personal view on that situation. That's the first question. And the second question is, I read your tweet or post in X, and you talked about assembly accuracy has improved significantly. Now, before the margin of error was 100 millimeters, but now it's down to 10 millimeters, and it's a significant improvement. How did that happen? I understand that you didn't make any significant change to the facilities, but what was the secret behind that, such a noticeable improvement?
So thank you for your question. So you are right, indeed. We are 1/3 through in the 1/3 through in the sector assembly, and now we are moving considerably faster. We have about 2 sectors every 6 months, as opposed to the very first sector that was installed many years ago. Well, many years was 2 years ago, with the one that we had to remove and repair, which took 1 sector more than 1 year. So we have increased a lot the speed, but once we will have installed all the 9 sectors, then the assembly is not finished. We will have to proceed with the welding of the sectors that we are currently preparing very carefully, because it will be a very delicate moment, and then the continuation of the assembly of all the external and internal components to the reactor. So, but we had a massive improvement in the speed with which we do work. The second thing is that we had to improve the way we would fabricate the field joint. The field joint, the parts neighboring 2 sectors, was imprecise, was not accurate enough. And so we had to repair it. And so we made sure, and was not a secret, it was simply that we had to set some repair facility on site, in order when we would receive the vacuum vessel sectors that had some weld distortions at the edge, we could repair them. And we made sure that this could be done in a way that would not add any time to the assembly phase. So no fundamental secret. Once again, I invite you to visit, and I will be able all to describe more in details these processes. Thank you.
ご説明ありがとうございます。おっしゃる通り3分の1完成した状況ですけれども、この進捗というのはかなり加速度的に進んでおります。2つのサブセクターを半年ごとに設置できているというスピード感です。2年前ではリペアなど問題があったものを取り除いてリペアしなければいけない、そういった作業もありましたので、一つのサブセクションを導入するのに1年以上かかっていたんですけれども、それから比較をすると、歴然たる改善が見られたというふうに思いますが、9つのセクターを全部導入したとしても、それで組み立てが終わりなわけではありません。その後には溶接という作業などもあり、これはかなり慎重を要する作業になりますし、外部内部の部品の設置、そういったことが控えております。そして2つ目の質問になりますけれども、この改善というのはですね、何も大きな施設の改善を行った、または何か特別なことをしたということではないんですけれども、現場でのパーツ部品の設置の作業の仕方というのを変えまして、ここで正確性を欠いていたところなどがあったんですけれども、そのリペア修繕できるようなファシリティというものを 整備しました。例えば、真空容器で歪みが発生していた場合には、現場で直ちに修繕できる、リペアできる、そういったような体制を整えることによって、改善に至ることができたと思っております。ということで、ぜひですね、ご自身でもITERに足を運んでいただきまして、その現場というのを見ていただきたいなというふうに思います。
はい、ありがとうございました。それでは続きまして、
Next question is from Mr. Izumikawa from Keidanren.
今日お話を聞いて非常にその進捗をしているというところで、当時、リペアを取り掛かろうとしていたので大変な工事だなという印象を持ったんですが、着実に進んでいることを見まして、改めて敬意を表したいと思います。質問ですけれども、この2年、ここ1、2年かなり抜本的に工事の進み方やコスト低減が図れていると思うんですが、そのあたりで何か取り組み上のマネージメント上の工夫なり、あるいはご苦労があればお聞かせいただきたいのが1点と、もう一つはこれからだんだんエンジニアリングに入っていったときに部分的な要素技術の技術課題の解決策を織り込んで技術開発を並行してやることと、それを新たにITERに織り込んでいく必要が出てくると思うんですが、そのあたりの取り組みについて日本に対する期待、あるいは関連するプロジェクトのメンバーに対する期待があれば合わせて教えていただければ幸いです。よろしくお願いします。
This is Izumikawa. 2 years ago, I had an opportunity to visit ITER myself. Thank you very much for having me at that time. And when I visited ITER 2 years ago, I saw the sheer size of the construction. You were having repair related work, and I was able to see that the massiveness of that work. Now I was very happy to see that you are making a steady progress, and I have 2 questions. And one is that 1 or 2 years ago, you had in the past, in 1 or 2 years, you made quite a big improvement in construction progress of the construction and cost reductions. I would like to know how you were able to do that. Did you change the way you manage the project, or did you introduce any new method or ideas to make that improvement? So that's one. And the second question is about engineering. I understand that now new technologies or technology will be used in ITER project, will be adopted in ITER project going forward as new technologies leave the research institute. Now you move on to the phase where you adopt them in a project. And when we come to that phase, I would like to know what is it that you expect from Japan or project members that what you expect from the project members?
Okay, thank you, Itsumisawa. And I remember well when you came with Tokura at ITER, and I hope you will come once again when you will be able to see better in the pit the assembly ongoing. Your first question is yes, it's a question we get frequently. What happened? What did you do? And there are a number of factors that played a role in our improved efficiency. I think very important has been the fact, the realization that ITER is a mixture of an international organization and a project. And I think that probably the first factor, the international organization per se, was overemphasized on the fact that it is also a construction project. The construction project needs to be organized in a way which is typically quite different from the organization of an international organization. And what I had to do with my collaborators is organize ITER as a construction project first. So We adopted a matrix organization, and we made sure that the right persons were in the right place. We have improved our processes and a number of other steps that each one of which could improve efficiency. I want to say also that we had to improve a lot the relationship with the regulator. The regulator was not trusting us, and the lack of trust from a regulator is introducing a tremendous amount of delays, because they will ask questions all the time, and they will, and rightly so, by the way, because if we are not trusted, they should, and that introduces also additional delays. So all in all, it's a package of factors that is allowing us to simplify, reduce the workload, and increase, say, the effectiveness of the organization. But I would say that your question would deserve probably a talk in itself, and I don't have time to go into all the details. That at some point it would be good to go to. The second question of yours is very interesting. ITER, as I said, has is a massive size and can allow also access from components. I think the main technology that we will have to develop around the world, in Japan and elsewhere, is the technology for the first wall, the technology for the blanket, because we will have with ITER a source, a neutron source that will be able to produce fusion power over a sustained amount of time to reach equilibrium. But we don't know, as I said before, yet we have not the proof on how we can sustain the power fluxes and at the same time breed the tritium that we will burn. And this is a type of technology which is it's being developed around the world, and ITER will provide a platform where we can test. We can test blankets, we can test them through the ports, we can test them elsewhere, and while we are doing the plasma physics that will allow us to optimize and hopefully to make the next machines cheaper, we will also be able, and we should be able, to test blankets to the maximum possible extent. Something that I really hope ITER will support. Thank you.
ご質問ありがとうございます。ITER にいらっしゃったことを私もよく覚えています。ぜひですね、またITERにいらしてその進捗というのをご自身の目で見ていただきたいなというふうに思います。最初の質問ですけれども、これもこの大幅な改善を遂げたということで、一体何をしたのというのを私たちもよく聞かれるんですが、この効率性の改善というのが実現に至ったにはいろんな背景がありますが、まず最初に気づいたということがありまして、これは多くの国際組織が関与した共同プロジェクトなんですけれども、今までは国際組織の共同プロジェクトというところに意識がいっておりました。しかし実際このプロジェクトというのはいわゆる建設プロジェクトなんです。国際的な組織、多くの組織が関わった特殊なプロジェクトというよりも、これは建設プロジェクトだ、ITER というのはすなわち建設プロジェクトだということに私たちは気づき、その気づきに基づいて組織改善などを行いました。適材適所に人を配置し、プロセスも改善し、建設プロジェクトというふうに扱うことによってプロジェクトの大幅な改善に至ることができました。また次にですね、規制当局との関係も改善したというのが我々のプロジェクトの進捗を進める要因にもなりました。かつてフランスの当局などはですね、我々のことを信頼していなかったので、いろんな質問攻めに遭いまして、それに対応するがためにいろんなプロジェクト遅延にもつながったということがありました。当然信頼されていないわけですから、いろんな質問をしてくるのは当然だというふうに思うんですけれども、それがプロジェクトの遅延につながっておりました。でそういった当局との関係が改善されたということもこのプロジェクトの進捗を後押ししてくれました。また業務量を減らす、簡素化する、そういった至るところに少しずつ改善を実施することによってこのような結果を を生むことができたと思っています。この詳しい話をし始めたらここでは時間が足りませんので、ぜひお会いしてですね、機会があれば詳しくお話ししたいなというふうに思っております。さあ次の2つ目の質問も非常に興味深い質問だと思います。これは巨大プロジェクトであり、メインのテクノロジー、を日本、世界に期待することとしては、ファーストウォール、ブランケットに関わるテクノロジーと、そして中性子源を使って、そのフュージョンパワーを実現する、そして並行を達成するということ、短期間ではできるんですけれども、これを持続させていくということになりますと、やはりまだ電力不足密度の問題ですとか、トリチウムの増殖という課題がまだあります。こういった課題に対して世界中、日本世界中で開発が進んではおりますが、それをテストする、ブランケットに関連する技術のテストをする、その施設としてITERを使ってほしいなというふうに思っております。プラズマの最適化に関わる装置をさらに安価に開発する、そういったことに関しましても、ぜひですね、そのITERの施設を使うことによって、さらに世界中のこのフュージョンに関わる開発の支援をITERとしてもしていきたいというふうに思っています。
はい、ありがとうございました。
Thank you very much. We are actually running out of time, but we would like to take this opportunity to just ask one student from the University of Tokyo, Yasuo-san, to ask a question.
ことを非常に感激いたしました。一方でですね、民間企業への技術供与というのもITER計画の重要な役割の一つとなっていることと存じております。そこでですね、世界全体で核融合発電を前に進めるために必要な公平でかつ平等な技術提供のための具体的な仕掛けはありますでしょうか。素晴らしい力強いプレゼンテーションありがとうございました。
Hello, my name is Oyabuso. I am a student, and I was actually so impressed by your presentation because I could learn that your project is smoothly making progress in line with the new baseline that you have established. And my question is related to providing your technologies to the private sector in order to promote the progress of your initiatives related to fusion energy at a global scale. The provision of your technologies that have been accumulated through your work needs to be shared in a fair and also equal manner. So I would like to ask you whether there's any kind of special system or mechanism to materialize this kind of fair and equal sharing of your technologies. Thank you.
Thank you for your question, and thank you for saying that we are proceeding smoothly. I don't know if it's smooth. I think we are proceeding. Nothing is smooth in a complex project like ITER, but thank you for your appreciation. So you see, the ITER project has 7 members. It's a project of cooperation in the world. It's a project of peace, but it's also a project of sharing of know-how. And since from its onset, all the intellectual property that was generated through the mechanism of ITER, through the project by the team, was equally shared with all the members. And it is available. It is available through our documentation system. And I will spend a few words now on that. So for me, when I joined, was important to consolidate this information and make sure that it would be available easily. So not only available in principle, but available easily. Now, a lot of information, particularly the success stories, have been published. You can find them, say, in the published material. Where it gets more difficult, and this is where I think we had to do some important work, was to share the stories of things that didn't really work very well. You know, in science and technology, and I'm glad that to some extent you asked this question. In science and technology, scientists are very happy about publishing information of good stories. But in development of a complex technology, all the failures are, let's call them like this, are also as important. So we have established now a way where the private sector, including the integrator, can access some specific channels in the ITER project, and they can ask specific questions on how this and that was done in ITER, so that we can go in the details which have not been published. So we can do better than that, of course, but there are also the 7 domestic agencies that have full access to the information, and this is completely shared, as you say, fairly. We have also set in place some methods to share some of the tools, the software that have been developed for ITER, for the modeling and for some engineering problems and the likes. We try to make this available to everybody so that once again ITER can be useful even today. Thank you.
ありがとうございました。それでは興味は尽きないところでございますけれども、時間も押してまいりましたので。
Even though we have many more questions that we would like to ask to you, we would like to end the Q&A session. Please a big round of applause to ITER Director General, Mr. Barabeski. Thank you so much. Thank you very much. Next, I would like to introduce the members who are now. Mr. Nishioka, the member of the House of Representatives. Thank you very much. Next, we would like to welcome Mr. Kazuhiro Sawada, Director, International Nuclear and Fusion Energy Affairs Division of Minister of Education, Culture, Sports, Science and Technology, and the Cabinet Office. Under the title of Fusion Energy Innovation Strategy, recent initiatives based on national strategy and domestic international trends. Over to you. Thank you for your introduction. My name is Sawada from MEX and Cabinet Office. I will give my presentation in Japanese, and I would like to notify you that several things. When I have talked about the fusion in Aomori, they requested me not to use the foreign imported languages. So I would like to refrain from doing that, and I would like to make my presentation impressive if possible. This is the table of contents of what I'm doing, policy trends, budget overview, and recent initiatives. Because I have two hats, I belong to MEX and also the Cabinet Office. So my presentation might be confusing because I might be going back and forth from two positions. And first of all, I would like to talk about policy trends in fusion energy. This is a kind of diagram that we have been using at MEX for a long time. We call it the mountain climbing diagram. Even though I have never been climbed Mount Fuji, this looks like it's making towards the top. We are at the middle, which is the scientific and technological materialization. What is next to the materialization of scientific scientific perspective. In this category, we have the ITER project as well as the JT60SI, as well as the ILL and Osaka University, and NIFS, which is at the Fusion Science Research Institute. And in addition to that, we are aiming at the yellow part, which is the government's goal towards 2030. And eventually, we would like to move on to the social implementation, of which goal is to be carried out by mid the 21st century. Currently, in addition to MEX, the Cabinet Office is now taking various measures. More specifically, we are supporting the SMEs, which is called SBER, Phase Innovation Research. And also, we are looking at the OST, NFIS, IoT innovation sites, as well as moonshot research development system. So in addition to QST, we want to add other institutions so that the ability of the startups will be concentrated in our initiative. I see many participant from the embassy, so I would like to explain about the background of fusion energy innovation strategy formulation. Members of the Diet has referred to the possibility of new fusion energy to solve both energy issues and environmental issues. Because I have a scientific background, I like to look at the technological aspect, but those in economy will focus on its possibility to enhance the business. I also have various opportunities to talk with people from the business community, which is quite stimulating for me. These are the two perspectives that the Japanese government is taking into account. And for this reason, the energy fusion energy innovation, which has been established, was updated as of last year. It's a kind of embarrassing to introduce you in front of participants from other countries. But first of all, the U.S. is taking various initiatives, including establishment of a new roadmap on fusion science and technology. And it is, again, it is capturing a huge volume of capital in which CFS is leading. And turning our eyes to UK, they are targeting another going forward by UK IFS. Germany, they are also focusing on research and infrastructure technology demonstration. France is focusing on ITER, as Dr. Barbeski has referred on. China, on the other hand, is focusing on the construction of a craft large-scale test facility. I hear that it's going to be completed in the near future. We are taking these into account and formulating our policies. Let's look at the case of the United States. It is said that compared to 2020, the private investment to fusion had increased by 10 times. Against the background in the Lawrence Institute, they have successfully completed their experiment of fusion energy. At the same time, in case of the United States, they have asked the questions to the academy related to the future course of the into the academy, and they have replied that generation capacity 50 megawatts or more, while keeping total construction costs below 5 to 6 billion was the definition that they need to pursue. And against this, the government will ask the companies to submit a roadmap, and when they are able to achieve what they have declared, then the government will pay the amount in return. And concurrently, the private sector is accumulating a lot of funds. Turning our eyes to the UK, they have the STEP program targeting the year 2040 as the year of generating electricity of 100 megawatts. We are now aware that we cannot lag behind other countries, and that is the reason why we have established the fusion energy innovation strategy. Shown on the photo is Ms. Takaichi, who have been in charge of the energy sector at that time, and many other members from J Fusion who may be familiar to you. And also the counterparts from the industry is also taking place in this initiatives. Like this, other countries, including US and China, they are proning their initiatives. And for this reason, in order to catch up with these countries, we have created the Integrated Innovation Strategy 2024. What you can see in this diagram on the left-hand side is developing the fusion energy, whereas the yellow part in the right-hand side is the strategy for technology. As Mr. Godot, who is from the House of Representatives, is here, who used to be a rugby player, so I was trying to think of an analogy of rugby. Fostering the industry and technology. Sometimes it may counter on one another, but if it's integrated in a proper manner, it's going to be extensive. And that can be implemented by the supporters for the audience in the soccer field, who will cheer the players. And so the government will play, the government and the ministry or play the role of giving the commands to how they can cooperate. And so by gathering the expertise that the private sector has together with what we have in the industry, we would like to establish the hubs. And also I heard some student in this audience who have asked a wonderful question, which can be support this initiative. This kind of a system for promotion, or it may represent a plasma, which plays a role that connect the development of the industry and the advancement of technology. Now I'd like to move on to the overview of the budget. Please be reminded that it's only a draft, because where this is where the ministry are, and I cannot declare that this is already set. We have been the MEX have been supplying the funds necessary for these initiatives. Fiscal 2025 will be ending in March. The budget is around 14 billion, but now it's going to increase more in the next fiscal year. And most of the funds are budgeted for the ITER project and the broader approach activities. Mr. Wakamatsu, as well as Dr. Barabaski, has also referred to this, that the initiatives is making progress. And also the Naka Institute for Future Energy and Technology has celebrated its 40th anniversary. As for the explanation of ITER, I would like to skip it, because this explanation was given earlier by Dr. Barabaski. This slide shows you the contribution of Japanese companies in terms of technology in the ITER project. The return that the Japanese companies can enjoy is around 80% in this project. This is quite extensively large compared to other international projects that's developed under the Japanese government. More than 300 private entities are involved in this project, and I am truly grateful to this. This shows you the ITER organization's structure. The Deputy Director General Kamata-san, as well as Okayama-san, Omae-san, and also Tada-san will soon assume the position of the chair of the ITER Council. In the ITER organization, we have discussions of increasing the staff from Japan. If you are interested in this project, please do contact our ministry as well as QST. Moving on to what the ITER Council is, I have attended in the November meeting, which was held last year, and the progress is always reported on this occasion. The production of the equipment is smoothly making progress, and assembly installation is making progress. Also, the delivery of the Japanese superconducting coils has also been completed. And for the BA approach activities, it's still sustained. And one of the highlights is the supercomputer that has started operations from this year. And also the demo director will also start a full operation like this year. The neutron, which will be sent in this project, is just like the rugby ball that is thrown in the field. And because of this energy, which is extremely high, this makes the future energy to be generated. And we have a new project related to the neutron base, which is called the DONUS. Spain and Croatia are involved in this process. And the left hand is another mixed funded project, which is implementing foundations for the demo reactor. This outlines the BA steering committee meeting. We also participated in this project. Next is about the budgets that is related to fusion energy research infrastructure. Again, the budget has been increased by 200 million for the coming fiscal year. And following next, the Ministry of Economy, Trade and Industry is also thinking of taking part in this initiative. In addition to tokamak reactors, the startups are now focusing on other type of reactors and now making proposals that this can be implemented, but they still have common issues such as how they can handle tritium. And this is not something that a single company is capable of dealing, which needs the support of the government. And the finance ministry have declared that they will support this by providing 325 million, so that arrangements will be made that the startups will be able to utilize. And I am thinking of executing this immediately. I'm sorry, this is actually the diagram that shows the initiatives of METI. They have ensured a budget of 60 billion. And they have, in addition to tokamak, they have helical reactors, laser type helical reactors. If they can be implemented, they can be effective. For this reason, they have secured a budget of 60 billion. And so the total budget for fusion energy is over 100 billion, adding the budget for the two ministry in addition to the finance ministry. Utilizing this budget, we would like to foster the necessary technology. Another new topic is to ensure security. And this is going to be delivered to the nuclear affairs regulatory authorities in the end. And the Cabinet Office have talked about the overall framework of safety and establish a task force to develop these discussions. And the third point is the scale project. This is about the legal regulations. And even though we have a set of regulations and laws related to nuclear power, but those applicable to fusion energy is not as strict compared to nuclear power. The specialists have developed discussions on 9 different occasions, and they are now trying to summarize and compile it into something more understandable. And the results is going to be summarized in coming March. This shows you the review task force for the social implementation of future energy. And even though the content that they are dealing is quite serious because it deals with how to implement social adaptation of fusion energy. Finally, this is the Moonshot Research and Development Program. This have designated as the 10th target. And we have made an overcall twice in last October and the year before that. And so we are going to select the candidates so that by 2050, through the multifaceted utilization of fusion energy, we will realize a vibrant society and being liberated from resource control. Now, this is a story that took place in October where the expo was held. On this occasion, the Emperor and Empress have visited the International Pavilion where the ITER booth was exhibited. The Emperor asked questions about the unique safety and its principle. And he asked a question more specifically referring to the most difficult part. On the other hand, the Emperor asked questions about the materials used in ITER, and Deputy Director General have answered a question, and they finally gave us a word of encouragement to make a project mistake. And in last year, at the Generative AI Preservation Society, entitled AI Academia First Presentation Meeting, Ms. Takaichi made a comment. On October the 11th, I took part in the commemoration ceremony, the 40th anniversary of the Research Institute of Fusion Energy and Technologies, where the Vice Minister have took part. And on that occasion, Minister of State for Special Missions, Ms. Onoda, kindly visited the institute, and I am grateful because she have took that opportunity. With this, I would like to end my presentation. Thank you very much.
Thank you very much, Mr. Sawada. Next, I'd like to have a presentation by Ms. Kashiwagi Mieko, the Deputy Manager of Tokamak System Technological Development Department of NATO Fusion Institute, on the progress of JT60SA enhancement for next operation and the ITER project. We have a live report from the JT60SA site. My name is Mieko Kashiwagi from KST Naka Fusion Institute. Until a year ago, I was responsible for ITER equipment. I am currently in charge of JT60SA equipment upgrade project. Today, I would like to report on the enhancement for JT60SA's plasma heating experiments, what achieved in 2025, along with the progress of the ITER project. The year 2025 marks the 40 years anniversary of the founding of Naka Fusion Institute. Amidst the rising expectation for fusion energy, we view that this year as one to renew our commitment to meeting such expectation. So I have depicted the burning sun from nuclear fusion rising from the summit of Japan's iconic Mount Fuji. This image represents our wish and resolve for further progress of this year. First, let me explain a path towards the demo reactor. At the Naka Fusion Institute, we achieved the world's highest ion temperature of 520 million degrees Celsius using using a JT60 experimental device. Building on that experience, we are now participating in a 7-polar ITER project currently underway in France. Furthermore, in BA activities that support ITER, we are going to conduct plasma experiment using JT60SA satellite Tomahawk project, and we are also engaged in the development of human resources necessary for demo reactor. Recently, under Japan's Fusion Energy Innovation Strategy, we have established Open Innovation Office in 2023 as a fusion technology innovation hub. Japan's JT60SA and ITER are the twin pillars of the pursuit of demo reactor. The diagram on the right shows future reactor output, plasma pressure index, beta N value, and the target regime for each equipment. ITER is close in size to demo reactor. Through this construction of the world's first high-performance large-scale device, it will acquire engineering technologies required for prototype reactor, and we will demonstrate stable operation from using the tritium as while considering safety, and we will also verify the technology. Whereas JT60SA is half the radius and the height of the ITER, but it is significantly larger than other tokamak devices in other countries. And so we would like to proceed with developing the plasma control and operational scenarios required in this area of beta N value of ITER ahead of ITER. Furthermore, we will test high-pressure plasma necessary for demo reactor, which is not included in an ITER project. Applying these results to demo reactor will lead to the prospect of economically viable reactor with a fusion power to heating input ratio of 20 to 30. We will approach the prototype reactor through two parallel approaches, developing ITER equipment and operation technologies at demo reactor scale and conducting challenging plasma operation tests at JT60SA. Now, in October 2023, the first plasma was achieved. It was the world's largest plasma and registered in the Guinness World Records. Then, starting in 2024, construction began to enhance the plasma heating system and prepare for operations at full-scale, high-temperature, high-pressure plasma. I will describe the progress of superconducting coils and heating systems later in the presentation. Additionally, we are installing the necessary power supplies, auxiliary equipment, and the devices for plasma control and high heat flux resistant components. Key manufacturers collaborating on these efforts are introduced here, with many more to follow. Measurement instruments developed jointly by Japan and Europe are also being delivered since last year. Additionally, last month, the crown-like upper stage was finally installed atop the JT60SA, and the instrumentation will be mounted on the stage. One critical task for the start of the next operation was strengthening insulation at the joints of superconducting coils. In March 2021, electrical discharges occurred at joints connecting the superconducting coil to the electrical circuit. So we needed some repair, but it was decided to reinforce the insulation at all similar locations. One item that required better insulation was a superconducting coil central solenoid. The problem was that the work area was inaccessible, located 6.8 meters high with a 70 millimeter gap. Initially, Europe proposed pulling the coil out for repair, but removal alone would have caused a delay of over 2 years. Japan proposed a method that avoid pulling out coils. We inserted the spray into a narrow gap to apply insulation resin. To achieve this, a mock-up simulating work site was prepared, and the spray repair method was developed. As a result, all insulation reinforcement was completed by summer of 2025. Preparation are also underway for two types of heating devices for the plasma heating experiment, which begins in 2026. The NBI, which heats plasma by injecting neutron particle beam, has 10 beam lines with varying beam power, beam energy, and beam injection directions. In the next operation, the injection power will reach 23.2 megawatts. Although this involves reusing old equipment, all beam lines are being returned to their original positions, and measures against aging and modification for longer pulses are being implemented. The problem is that the Japanese products are so good that the 40-year-old equipment still functions, while control boards and small electrical components have deteriorated over time and become unusable. So they needed to be partially replaced. There need to be major replacements, so I appreciate your cooperation. And for the update, I'd like to give the cooperation from the various makers. Another heating device is RF heating system that heats plasma using high frequency. We had 2 units. We added 2 more to a total of 4. This system will also contribute to plasma experiments by utilizing gyrotron with different frequencies. And we also would like to report on 2 fronts of the plasma control. First, the completion of the fast plasma positioning coil, or FPPC, which is essential for keeping the world's largest plasma in JT60SA stable. Mitsubishi Electric made a joint media announcement. FPPC consists of top and bottom copper coils, each 8 meters in diameter, inside a vessel. And from the perspective of good control plasma, locational as well as dimensional accuracy within plus or minus 2 millimeters is required. During manufacturing, we had to introduce the conductor into the vessel through this narrow port and wind the coil in a tight space where numerous other devices had already been installed. We experienced some setback during manufacturing, but by modifying jigs and other measures, we eventually met accuracy requirements. Establishing this technology will contribute to ITER, as ITER also has coils inside a tight vessel. The second point is the development of the world's first AI-based plasma confinement magnetic field prediction technology, which we jointly announced with NTT to media. Previously, we constructed magnetic field shapes from data gathered by measuring equipment needed iterative calculations. With AI-based prediction, results are reproduced in real time and achieving a high precision reconstruction with an accuracy of approximately 1 centimeter. So the field changes with time, so the reproduction was initially difficult. However, we introduced a mixed expert model, or MOE. This model consists of AI that comprehends the whole system and provides command control. It's like an orchestra led by the conductor. Each instrument plays a variable volume of the sound that together create a one piece of work. This approach was able to reproduce magnetic fields quickly with extra high accuracy, something single AI program cannot do. So at this time, let's look at what's happening on the floor of JT68 manufacturing. Mr. Takahashi is General Manager of the Tokamak System Technology Development Department. Please switch the screen. Mr. Takahashi, please explain what's happening there. Can you hear me? Yes. Further to last year, I would like to give a live reporting from JT60SA site. I'm in front of the JT60SA. So I'll show you the inside the vacuum vessel. This is a JT60SA. It stands about 16 meters tall and is about 13 meters wide. It weighs about 2,600 tons. JT60SA achieved its first plasma in 2023, setting the world record of plasma volume. Starting in 2024, we began equipment enhancement work, installing numerous pieces of devices both inside and outside the vessel in preparation for full-scale plasma heating experiments. For example, the pipe is about 60 centimeters in diameter, runs from the right to left, and connects to the vessel. Inside the vessel is a Thomson scattering device. It detects weak light scattered when laser lights collide with the plasma electrons when the laser passes through the plasma. So the Thomson scattering evaluates the plasma electron density and temperature. This device is called Thomson scattering, and the piping is a part of that system. So the moderator of this symposium is in charge of this Thomson scattering. What's more, over the past year, the NBI, or neutron beam injection system, was installed. A large platform for mounting instruments and other devices equipment was set up on the tokamak. Furthermore, the restoration of the shielding wall necessary for fusion experiment has been completed. I am at the entrance of the vacuum container vessel. Can you see it? So we'll enter here, and please look at the inside the vacuum vessel. I'm inside the vacuum vessel. Can you see it? Yes. So we are inside the vacuum. It is 6 meters high and 3 meters wide. And we are currently in the center of the vessel. And there are coils that control the position and shape of the plasma inside the vessel. As Ms. Kashiwagi explained, among them is a fast plasma positioning control coil, or FPPC. That installation is completed. So when manufacturing it, we inserted the conductor from here, and we had to wind coils in a very tight place. Thanks to Mitsubishi Electric, it was completed late last year in December, and we made a press release. We'd like to hear comments from Mr. Okada, a medical personnel who worked on it. My name is Okada from Mitsubishi Electric. This is a coil, FPPC coil. It is about the same size as a vessel, so within a confined space, we had to wind the coils. We use a dial gauge and a laser tracker to alleviate the problem, and this represents the precision of the plus minus 0.05% of the target specification. Thank you, Mr. Okada. The successful fabrication and installation of this coil with a high precision within a plus or minus 2 millimeters will significantly contribute to improving plasma performance in a future experiment. Furthermore, since similar technology will be required for ITER, so internationally this would mean a great outcome. Next, we will install equipment that will be directly exposed to high heat of plasma inside the vacuum, such as diverter and first wall. I will ask Mr. Sasajima from Sukegawa Electric for some comments. My name is Sasajima from Sukegawa Electric. Sukegawa Electric is now trying to use install the fixed table for diverter. That it has to have the accuracy of plus minus 1 millimeter. We are close to the finishing the installation. Thank you, Mr. Sasajima. Inside the vacuum vessel, you may find it a lot larger than you expected, but considered with compared with working in a factory, there are many constraints. So there are some unexpected things happened, but we resolved the issue one by one, and we have been proceeding with this installation. In the latter part of the installation, in parallel with that, we also need to operate and test the equipment that had been already installed by autumn of this year. We aim to start plasma experiments by the end of this year. Mitsubishi Electric and Sukegawa Electric and Hitachi and Kurihara, and there are many companies who are cooperating with us on this front, and we'd like to continue to work with them closely. We'd appreciate their continued cooperation. This concludes the live streaming from the JT60 SA site. We'll now return to Kashiwagi-san in Tokyo. Thank you very much. They are currently working around the clock, including weekends, to proceed with the construction. Next, I will report on the ITER project. We've seen a significant progress in construction at the ITER site. In 2025, 3 vacuum vessel sectors were delivered to the tokamak pit. This represents 1/3 of the entire vacuum vessel. Each sector has 2 toroidal field coils and is massive structure standing 60 meters tall and weighing 1,350 tons, the weight of 3 passenger jets. Installing them with 1 mm accuracy requires extreme advanced techniques. For this task, personnel from QST, including those responsible for superconducting coil fabrication and assembly team members from the JT60 SAA, is joining the ITER organization. Initially, it took 18 months per unit from assembly to installation. Currently, we have reduced this to 1/3 of the original target and are aiming for reducing more. Here is an overview of what Japan is supplying to the ITER project. Japan is supplying technologically advanced key equipment, including remote handling machine for blanket, diverters, tritium plant, all conductors for the central solenoid, toroidal coils, gyrotron, and launchers for high-frequency heating system, plasma management instrument, and there are more makers who are cooperating with us. After at the ITER site, we have seen a completion of installation of first gyrotron unit. So it is going through the water flow test and other procedures. A slew of manufacturers participated in the development shown on the screen. And at the ITER site, there have been progress in base technologies for demo reactor. These are the cooperating companies. At the ITER site, preparations are underway for cold testing to cool the toroidal field coils supplied by Japan and verify their superconducting capability. This photo shows a coil lifted up and installed inside the test cryostat using this yellow chip. Verifying the performance of the Japanese-made coils ahead of ITER operation contributes to the development of base technology for the ITER-scale demo reactor in Japan. The diverters are subjected to thermal load higher than what's expected at the time of re-entry into the atmosphere. Japan will manufacture all 54 outer vertical targets, or OVT. They are exposed to extra high heat. Manufacturers of OVT components listed here are all Japanese companies. The European Union ordered tungsten monoblocks from Japan and already received them. The EU also made inquiries about other parts such as copper alloy tubes and twist tapes. In Japan's equipment manufacturing, Hitachi's prototype has already been completed. Mitsubishi Heavy Industries' first unit has been finished and already in the mass production phase. Their performance is being verified by the thermal load test device designated by the ITER organization. Daido Steel, which will make presentation today, is among the contributing makers. Since ITER walls utilize tungsten, experiments on tungsten walls are being conducted at tokamak worldwide. These efforts will significantly enhance preparation for ITER operation and outlook for the demo reactor. The blanket remote handling and the remote maintenance development tools shown in this photo will be utilized during ITER's initial assembly. A procurement agreement was signed in August 2025. It will help pull forward the start of ITER operation. Sugino Machine, which will give a presentation in a minute, is among contributing makers. Construction of a neutron beam injector MBI is progressing at NBTF test facility in Italy. During a 1 million volt power supply test, equipment was damaged because of overvoltage caused by insulation breakdown. Since then, we have almost completed the manufacturing of prototype equipment to safeguard devices. And here are a list of manufacturers producing equipment related to 1 million volt systems. Finally, the next 3 pages will introduce the cooperative framework and human resource development. First, the JT60SA experiment team has been formed. The team has a Japanese experiment leader serving as a coordinator with 1 leader each from Japan and Europe. And the leader for each experiment team are composed of personnel from both Japan and Europe. ITER has expressed interest in participating in the experiment. we have conducted a cooperation agreement that enable two-way exchanges. Another way to participate in these JT60 SA project experiment is through joint research initiatives. Under ITER project, there's a direct avenue to participate ITER itself. Applications can be submitted through the ITER's Japan Domestic Agency at QST for ITER staff, expert dispatch, and internship program for high school students. Here are some main research collaborations. This fiscal year, we held presentations at various locations regarding on-site lab agreement. The initiative promotes collaboration and talent development at the other institute in the JT60 SA. It provides a space for Naka Fusion Institute where professors and students can stay and participate in a discussion. We have concluded the agreement with 10 universities and research institutes listed here. Every year, there is a call for proposals for tokamak core plasma research. Proposals are solicited for themes related to JT60A experiments. The call for next year has been already closed, but there were 17 themes. International cooperation agreements were concluded with 2 U.S. institutions. Now we like to introduce 2 schools. One is the third JT60SA International Fusion School, or JEFS. We are offering seats for 26 students from Japan and Europe, and experts from Japan and the EU give lectures. The program includes a 2-week intensive lecture program and practical training at the Naka Fusion Institute. Furthermore, it also has a tour of domestic research facilities. This week, as we speak, participants are visiting European Research Institute for special practical training. The second school is a school catering to women. One initiative was adopted at SNF's educational program, and where we recruited the participant equivalent to university freshmen or above who are interested in fusion energy. Over 50 women participated. Although this was the first attempt, participants demonstrated remarkable enthusiasm in considering their future career paths. So we should continue this program. Finally, this is what we do at the Naka Fusion Institute, developing technologies for construction fusion device using JT60 SA and developing the plasma performance required for the demo reactors through plasma heating experiments slated to start in 2026. And the ITER project, we will demonstrate manufacturing of the large-scale equipment required for the demo reactor and stable operation technologies, and advance the development of the supply chain for manufacturing the demo reactor. Leveraging this platform and collaborating with the Rokkasho Fusion Institute, the research hub for the demo reactor, we will advance towards Japan's prototype reactor for established technology, developing human resources, and fostering cooperation with the manufacturing and the startup. Thank you.
Thank you. Next presenter is Mr. Yoshiteru Sakamoto from QST Rokkasho Fusion Energy, and he will be talking to us about activities toward JA demo aimed at demonstrating power generation in the 2030s. Good afternoon, everyone. I am Sakamoto from Rokkasho Fusion Energy Institute, and I like to present about realizing demonstrating power generation in a 2030 as government targets. And ITER size demo reactor, and what we are doing at our institutes is the present part, main part of my presentation. And Rokkasho Fusion Energy Institute is surrounded by rich nature, as you can see in the picture. And you see mega solar power plant, which looks like a lake. And also we have wind power plants, which are look like street trees. And I think this is a very good place to study future energies, such as fusion energy. And for us to generate power using fusion reactor, there are three major challenges. One is that to trigger fusion reaction, we have to be able to manage burning plasma in a stable manner. And as QST, it was reported, as it was voted, ITER and JT60SA are working on this topic. And Naka Institute is leading the charge. And the second challenge is to extract generated energy and the creation of fuel. And this is something also Rokkasho Institute is leading the charge. And we have a broader approach, BA IFAC project. We design demo reactor R&D, we manage supercomputers, and we also perform ITER remote experiment. In IFMIF and IVEDA project, we are developing the world's largest current accelerator for material irradiation facilities, and also blanket. We are working on ITER test blanket module plan or planning. And now I'd like to talk about the future of fusion energy. And for us to be carbon neutral, there's an energy scenario performed, and according to the analysis, if in 2050 fusion energy is introduced, in 2100 fusion energy will be responsible for more than 30% of total energy in Japan. So when it comes to sustainability, fusion energy is very vital for us to realize a sustainable future. And fusion reactor, with fusion reactor, if the fusion reactor plays important role, then energies in major cities, the fusion energy can supply stable base load energy to big cities. And so it is extremely important for us to be able to demonstrate power generation in 2030 as the government aims in its strategy. And QST, before the middle of this century, we had a plan to demo reactor, but following the government strategy, we are trying to accelerate that time schedule. So there are two things for us to move this forward. First one is, of course, and we need to design demo reactor which we can build at the shortest time scale, and we are going to use the ITER technology to a maximum, and then fill the gap between future technology and existing technologies. And for superconductor coils, it can take forever to design and produce. And if we use ITER superconductor coils, then we can reduce the time and workload for R&D and implementation. That will help us implement this plan with the shortest amount of time. And the second is that multi-phased operation needs to be planned. We are targeting 2030s, and after we need to demonstrate first, and then blanket that needs to be exchanged on a regular basis. Our plan is to, in a phased approach, to improve blanket performance and plasma performance. And with that, gradually we should be able to produce 100 megawatt of net electricity and utilization rate and self-sufficiency of fuel. But here we have to think about that what we are doing has to be significant, and technologically and scientifically we have to make something that is meaningful. And this is the This slide talks about scientifically and technologically significant power generation to be demonstrated in the 2030s. And scientifically speaking, it has to be burning plasma with higher self-burning ratio. And helium alpha particles, by using alpha particles to have the plasma to self-heat, we should be able to maintain burning plasma. And the self-heating ratio is more than 2/3. If the ITER size demo, it is possible to realize burning plasma with higher self-heat ratio. And also to build a commercial reactor, it is important to be able to produce net electricity output. And fusion reactor plasma heat and superconductor coil to cool superconductor coils, we need a lot of electricity. Even though its net electricity is zero, it's the hundreds of thousand kilowatt of power generation turbines output. Even though its net electricity is zero, we can improve net electricity by optimizing or streamlining these systems. And ITER produces 500 megawatt of nuclear fusion output, and we believe that ITER size demo reactor is possible. And this slide shows our targets in the using of equipment and machinery, a multi-phased approach. And the first phase is to demonstrate power generation, and the second phase is breed fuel. The third phase is to realize constant operation. In the first phase, about power generation demonstration, we install blanket specialized for power generation so that we should be able to secure ITER sized or plasma volume, and Q equal 10 plasma should be achieved. And if we can do that, then like ITER, short pulse operation for a few minutes will be achievable. That's the net electricity zero. And the second is to exchange blanket for fuel breeding, and that plasma, we raise plasma pressure and we operate long pulse operation to breed fuel. That's the second phase. And the third phase is that we will reflect research and development, and we can implement a blanket, and then JT60SA achievement can be reflected in this project, and to achieve 100,000 kilowatt. And then we can also test self-sufficiency fuel. And this slide is the ITER size demo reactor demonstration in 2030 and the path to commercial reactor. ITER size demo reactor, ITER and demo reactor, that we have to narrow the gap between those two. And by narrowing the gap with low risk, we can accelerate demonstration. And on the other hand, the demo reactor and the commercial reactor, the gap could be wider. But to address this issue, ITER and BA activities, based on BA activities, we will take a path from moving from demo reactor to commercial reactor. That's the blue arrow. And on top of that, using fusion innovation strategy, we can develop technologies necessary for implementation into society. So this is the way to reduce the gap between demo reactor and commercial reactor. This is the timeline. And for us to achieve power generation demonstration 2030, ITER and JT60SA construction assembly operation, those experience need to be used to a max, and we also join forces across industries to build a demo reactor. And also QST will use research and institution facilities. Will work with the academia and universities and to expand development of fusion machinery. And also with ITER, with real twin high plasma performance operation has to be realized with limited risk. And from now on, I would like to focus on what we are doing and our achievements at Rokkasho Institute. And first, about designing prototype reactor. And we have a special team participated by industry and academia. And this team was launched in June 2015. And recently, based on the fusion energy innovation, we have expanded more members, firms. We have more firms on board, and we are reinforcing partnership between industry and academia. We have 47 firms and 25 universities and 7 institutes participating in this team. And in total, we have 200 researchers and engineers are working on this topic. And the ITER size prototype conceptual design, JA demo that this special team has been working on. And this is the guide. This is the its plasma is 8.5 meters, and with the conceptual design and the ITER real design that is being in construction, that we can organically combine those two projects, and we are hoping to be able to complete the conceptual designing before the end of this year. And next is this is the activity to build a prototype reactor. This is the international standardization by basic guideline for safety. We have a bridge project for Society 5.0, and the QST we would like to be the main actor for international standardization, and we are promoting the meat of the plan, formulating the pillars of the plan, and we're also developing young talent. And we signed JSME and ASME signed a partnership agreement. And when standardization, we are in the middle of formulating international standardization, and also to secure safety, basic plan to secure basic plan, together with nuclear regulatory agency. We have been in close communication with the agency, and ITER size reactor schedule and fuel cycle system, tritium handling, and basic safety policies. Those are the things that we exchanged with the agency, and that agency before the end of this year, they are going to summarize their concerns. Next is ITER TBM plan. At the heat load experiment, using the ITER requirements, we irradiated electron beam and then tested cooling performance. As a result of that, according to the plan, we confirmed that we were able to remove the heat, and rupture disk within a subjoule pipe rupture. The water leak is something we tested. We perform mock test and use trace code. The results are in line with the trace code, but there was for temperature or pressure fluctuation, we are still working on the results. And to acquire TB system final approval, we are in testing. We are performing a safety. And next is breathing blanket, lithium recovery, and beryllium recovery, or for lithium recovery technology. We use ceramic film, that is ion conductor, to recover lithium. And in the past, once lithium is recovered, the lithium, the concentration of it goes down. You can see the blue, the total flux goes down against this backdrop. That once lithium is recovered, the recovered solution and the original solution, we created a system to circulate together the solution before and after recovery. And we have established a method that concentration will not affect the results. And now we can test the ion conductor performance correctly. And with lithium concentration, we establish conditions to improve separation factor. In the low temperature refinement technology, beryllium or a solution of beryllium, we were able to recover single phase beryllium hydroxide. And here XRD is indicated here on this page, and you can see that we were able to recover single phase beryllium hydroxide. And also in our Mori, the team, now we are in discussion of land for building industry, and QSD certified venture listed Mireso, our collaborators in developing these technologies. Next is the activities toward a fusion neutron source at QST. Together with Europe, we are working with Europe. IFMIF prototype accelerators is being developed, and we are in the home stretch. And the target is to Q9 mega electron volt heavy proton beam accelerator, and superconductor high frequency accelerator SRF has already been delivered. With that, total length of 36 meters of beam line will complete. And also in Europe, IFMIF DONES program, Japan will be joining this plan. And as a executor, QSD as an executor in Japan, blanket structure materials of neutral irradiation data will be should be available for us. Now we just signed all the arrangements with the relevant agencies. And next is activities toward a fusion informatics center and a prototype reactor. And for a future commercial reactor, we need highly autonomous burning plasma controlled, and using digital twin, we need a highly advanced control technology. And at our fusion informatics center, we use ITER experiment data and large scale simulation data and data-driven science. We use these different data to perform our research. And in the BA activity, we have a calculator simulation center, and ITER remote experiment center will be integrated with Fusion Science Data Center to work on this. And at Rokkasho Institute, we started the third generation supercomputer operation gym. And this is the supercomputer together with the fusion Science Institute together with this. The performance is 10 times better than the second generation. On this computer, we build LHD digital twin, and using digital twin, we forecast the physics volume that we never measured before, and in a real-time control experiment is going well. And this is the joint effort with different institutes. And the last but not least, this is the activities about activities on fuel cycle system. And for fuel cycle system, we never had an experience of developing or testing high concentration of tritium, processing deuterium and tritium in the mixed pellet. And here, prototype reactor fuel cycle miniature plant was built. And for legislation, it is important to gain our experience on handling tritium. And we were working on the building concept. And now, this year, we need to survey potential buried cultural property of the land and boring survey. And through the designing and construction, this place will be a fusion technology innovation hub. At QST, but the government stated that 2030, but before 2030, power generation needs to be demonstrated, and to that end, we'll continue to work on fusion energy, and also we build a fusion energy hub so that industry and academia can make the best of the facilities, and we'll continue to pursue this goal. So I appreciate your support. Thank you very much. Thank you.
With this, we completed all the keynote lectures. We would like to take a short break before the special lecture. The special lecture will start at 4:15. Please be seated before the starting time. Thank you. Thank you very much for your waiting. Now we will like to start the latter half of the annual Symposium 2025 on the ITER MBA activities. I would now like to introduce the honorable guest attending this meeting. The member of the House of Representatives, Mr. Daichi Suzuki. Thank you very much.
Next section, we move on to presentations on technology. For us to realize fusion energy as early as possible, we need everyone's help from industry and ITER plan and BA activity and the development of prototype reactors. We have 4 companies to present how they are contributing to this effort. And we start with Mr. Koichi Uno from MIS, and he belongs to platform development team. Thank you for your introduction, and I am from MIS. My name is Uno, and here I am to talk about development of integrator system for plasma control. And this is those are my agenda items. First, I like to introduce who we are, and then measurement of plasma shape and development of the integrator system, and conclusion. And MIS Corporation, we are called MIS Corporation, and we have 79 employees. So we are a small, mid-sized company. And our main businesses, a line of business, we have DSP, IPC, and vibration business. So we have 3 lines of business, and DSP business is where we develop integrator system and produce manufacture integrator systems. In the DSP business, DSP and RMBD, we prototype systems and prototype these products and manufacture at the scale. And we also use model design. In RCP Hills, in a development phase, real-time simulation environment is available. And next, IPC business in long term, we design and produce industrial computers and embedded computers and in touch panel monitors for industry. And vibration business, here we have vibration test controllers and vibration test software are what we produce. And here's the main part of my talk. And for measurement of plasma shape in tokamak fusion reactor, there are some requirements that need to meet. First is we need a sensor that is highly tolerant for high energy neutron irradiation, and we have to be able to produce high accurate measurement value. And we participated the second requirement, and the first sensors were magnetic measurement sensors, and the major sensor is Hall sensor, but it is used by semiconductors, and it is not tolerant to neutrons. And we need something that is more neutron tolerant, and we use solar rate coil. Solar rate coil is what we call the electromagnetic sensor. And when the sensor, the field changes, it produces voltage according to Faraday's law. And output voltage, we need to time integrate to calculate the field, magnetic field. And the second is measurement system. Is with high accuracy. We need to time integrate as a measurement element. We use VF converter with integrated circuit embedded. This is the diagram, simple diagram of VF circuit. This is the integrator circuit, and we use comparator to perform comparison, and then we output as in pulse signals. And the VF converter, depending on the voltage, the output signals frequency will change, and with low conversion latency, we can produce digital value. And this shows where our product is used in JT60SA. It's installed inside a blanket. And the pictures, those pictures show where our product is installed. And also inside of vacuum vessel, I understand that there are so many different sensors are being installed. And then electromagnetic sensors to analyze signals. Left-hand side, this is our time integrator system. And this integrator system is made of VF converter. And from a sensor, signals plus minus 1 volt and plus minus 10 volt and plus minus 5 volt. And it is simultaneously converted in frequencies. And next one is digital integrator board. And the pulse signals sent by VF converter will be counted, and then count value will be updated for each cycle. And a system controller and a reflective memory board. And digital integrator board count value is read out, and count value is calculated into frequency. And then it is sent to memory, and the upper system that control plasma can manage sensor values, multiple sensor values altogether. And this is the integrator system. You see how our integrator system is made of, and integrator system on the right-hand side is the picture that we zoomed in on, and you cannot see it very well. The board here is the system controller diffractive memory board, and this is the digital integrator system. That's the VF converter. And then this is the measurement. This page shows the measurement data. A is coil current time change, and electromagnetic sensor noise content is it's B. And so it changes over time, and the phenomena called drift is happening, and that drift needs to be high pass filter. The C is the with high pass filter to remove the drift. And just for your reference, 100,000 seconds long duration integration assessment is performed. This is 0V input, not electromagnetic sensor input. And for long duration integration, due to temperature and power voltage fluctuation, chiral errors are accumulated, and that create dispersion of outcomes. But using stable power, we were able to control and converter temperature. And this is only our test results, but the performance by JT60SA, its requirement is more than 1,000 seconds, and we were able to prove that in our internal experiment. Thank you. Thank you.
Thank you very much, Mr. Uno. Next, from Sugino Machine, we would like to invite Mr. Oikawa Shiro from Plant Equipment Business Division at PE Technology Headquarters. Nice to meet you all. I am Oika from Sugino Machine. I have come here from the northern part of Japan, Toyama Prefecture. My presentation is related to nuclear power and nuclear fusion. For the places where humans are not able to access, we have provided various solutions, and we are now working on the approach for first of all remote handling, and this is the topic of my presentation. In the first half of my presentation, I will explain the company profile, and in the latter half, I will explain the front wall remote handling. This is the company profile. We were established in 1935, commemorating the 90th anniversary. Located in Amerikawa, Toyama Prefecture, in the middle of Japan, surrounded by the sea and forest. As to what we do, we develop, design, manufacture, and sell industry machinery, machine tools, and power plant inspection and maintenance equipment. In response to the request of our customer, we can create the desired product from scratch. That is a strength. Now, I'd like to move on to the technologies that we have. Together with the customer, we were able to create the technologies which had evolved in the past years, then developing into various areas. For example, the cutting technology. We utilize the auto high pressure energy to cut various things. In addition to that, washing, automizing, machining, fibrating, and burnishing are the technologies that we provide. Next is the chain of product. Our origin is the tube cleaner in the 1940s. That is the skills that remove the clogged pipes. And from that, four devices have been created. The devices that we provided cover a wide range of areas. We have been able to develop by responding to the needs of our customers. Next is the business fields that we offer. The products that we offer is not actually visible to the customers, but it covers a variety of fields. Automotive, aircraft industry, pharmaceuticals, and cosmetics are the representative fields. More than 5,000 companies are the customers that we provide our products with. Next is what we can handle. We are able to develop and commercialize equipment system to safely, efficiently, and reliably operate and maintain integrity of our nuclear facilities and power plants. Then we are able to create it from front end to back end. Even though we are not able to introduce to you everything, we will introduce some of them. This is a crawler type multi-joint industrial robot, which can access other places where human cannot. The output in maximum is approximately 100 kilometers per hour. It can be charged by a battery. That is the reason why it can be operated in a remote setting. And the work related to nuclear facilities to be certain about this job is important. In order to check the facility as much as possible in a circumstance closer to the actual circumstance, we created the task for water depth simulation with a height of 60 meters, 27 meters in depth, and capable of accommodating the material over the size as shown in this slide. Next, moving on to the first wall remote handling tools. This is an enlarged photo of the vacuum vessel. It is created by the first wall. It covers the vessel. And it is possible that it gets in contact with the plasma, and in that case, it requires a replacement. And we have created prototypes so that our machinery will be able to undertake this job. This shows you the configuration of the blanket, and the shield block, the first wall, is connected with the bolt, and in between there's the end cap and cooling pipe. For this reasons, in order to remove it and to assemble it once again, a long process is required. This shows you the maintenance in the vacuum vessel. The vehicle manipulator is inside the vacuum vessel, and the remote control device will be inserted in between. And there are certain positions requires remote operation positional accuracy, and also there because of the various types of the first walls, we need to be able to accommodate to them. Tsugino machine, we started with a conceptual design with the remote device, and then move on to various prototypes. In 2020, we took part in the demo reactor maintenance design. In 2021, we have also started to design the initial a series of tools related to the assembly of the ITER project. First, when we connect the walls, we prototype to verify the roller type and a pad expanding type, which will be adaptable to adjust the gap between the two. And actually, we have created these two types, and in the end, we adopted the pushing pad. This was an application of our company's pipe expansion tool technology. Next is pipe cutting tool prototype. We have to cut it and finish it as smooth as possible so that it can be connected once again. And for this reason, we have applied the pipe cutter in the very end, in the tip of the tool. As we conducted the tool, we could confirm that we are able to cut the pipe from the interior. This is the tool fixing mechanism prototype. Due to the constraint of our time, I will skip the explanation for this. With this, I would like to end the preparation of the mechanism that we have dealt on. Next is about the approach for initial assembly tools. This is the tool that will be indispensable for assembly the reactor during ITER construction. Utilizing the experience and expertise that we have accumulated throughout the years, FW remote maintenance tools became the starting for the initial assembly tools. This is the summary. Sugino machine has leveraged its long history of experience in nuclear power to participate in ITER. We have continuously designed, developed, and prototyped remote maintenance tools for first wall, and are also advancing the development of tools for initial assembly. We will contribute to the advancement and stable operation of fusion energy, starting with ITER through remote maintenance technology. This is our vision, the global niche leader. From a local area in Toyama Prefecture, we'll be able to send out information towards the world so that we can become a niche leader in the global arena. Please get in touch with us if there's anything that we can be of your use. Thank you very much for your kind attention.
Thank you very much, Mr. Oikawa. Next presenter is Mr. Masumoto Ryoji, Deputy Head of the Raw Materials Solution Planning and Development Division, Raw Material Department of Daido Steel. Mr. Masumoto, the floor is yours. Thank you for your kind introduction. My name is Matsumoto from Daido Steel. Thank you very much for giving me opportunity to make presentation. From 2010, we have been providing the steel materials, especially the forged materials, to QST and other makers. Today, I will talk about the overview, giving an overview of our company and initiatives that we are engaged in. This is the agenda for this presentation, 4 items. Introduction of Daido Steel and activity to manufacture materials for ITER products and some products that are characteristic of our company. Our company was founded over 100 years ago, 1916, and we have merged 3 companies in the 1970s and become the Daido Steel. And we have Nagoya, Tokyo headquarters. In Osaka and Fukuoka and are the main headquarters. And in Chukyo and Kanto district regions are our main area, and rolling products are the Chita and Nagoya. And let me share with you our products. Stainless steel, round steel bar and square bars, and metal powder, and titanium alloys, and magnetic materials, and applications for the aircraft ship, and we also make industrial parts for aircraft ships. So Shibukawa plant is a main plant to produce forged materials for the ITER project. And the melting equipment is EAF and AOD, and the refining, the vacuum induction melting and EAF is used for melting, and AOD is for refining, and the SVR, VER are also the melting, and we have one of the world's best melting equipment. We deal with the stainless steel and nickel alloy, and depending on the production lot, we will combine the various melting facilities to come up with the optimum process for the product. And we have the forging equipment is ranging from 1,500 to 1,700 tons. And we will do also the non-destructive test, NDT. And we have an integrated production process to provide high-quality products. So these are the shapes of our products: disc, ring, pipe, and step shaft, and flat bar. Applications are aircraft, nuclear power facilities, drilling, and semiconductors and drilling. The product sizes are different depending on the materials. Disc and rings, 3,400 millimeters. For pipe and shaft, up to 1,300 millimeters. So melting and forging technology, our expertise in those areas can produce a variety of products. Next, I'd like to talk about the materials we provide to ITER project. So the forged product is a toroidal field coil and diverter. We produce components for these two things, TF coil and the diverters. The components for TF coils are threefold. One is to superconductive conductors jackets. So the round bar, the 316N steel, the drawn materials. The second one is a radial plate, the forging plate for TF coils, and also round bars and a forged plate for TF coil structure. Heavy industry companies will do final machining to become the final components. So this is the history of our initiative to provide products to ITER. So we have a prototype 316N steel for diverter prototype. F82H for the TBM products. And starting from 2012 to 2017, we produced 10 of them. And the radial plate, we produced all the 9 radial plates that is in charge by Japan. We produced all of them. So steel products and for ITER project, we have already delivered 4,400 to 4,500 tons of steel products to the ITER project. We are still producing materials for diverters. Let me share with you our main products. One is a radial plate materials. As you know, the one plate is divided into 10 parts and welded, and 7 plates are piled with the conductors in between the plates. So most difficult part is A1 and A4 segments that with an angle of bent of 90 degrees. So yield was very poor and production efficiency was low. So our challenge was how to improve them. At the research institute in Nagoya, so we simulated jigs and tools to produce it, and we have established a technology to bend longitudinal bend at 90 degrees. And that contributed to improvement in yield and efficiency. And we have produced 630 such plates altogether. The second one is the OVT materials, outer vertical targets for diverter. XM90 support is our components are for SM90 support and 316N structure material. So the specification required are threefold. One is the impurity removal, and so that we can have a low radiation. And also the molybdenum control. And we need to have the high cleanliness through the stringent refining process. So we use top of the line smelting technology. So we have already delivered 33 cassettes of forged products, and we are producing 25 cassettes more. So in 2010, we began producing the products for toroidal coil forged materials to the ITER. And some of them are still in production. So for the horizontal port launcher and test blanket module, we continue to produce and deliver components for that and material for that. And we will make efforts to further improve our quality of our products. Thank you.
Thank you, Mr. Masumoto. Next presenter is from NEC Corporation, Director of HPC Division, Mr. Shinkami Yamane. Please come up onto the stage. Thank you for your introduction. And I am Shinkami Yamane from the HPC division of NEC, and thank you very much for giving me this opportunity. And I like to talk about the new supercomputer plasma simulator and NEC's initiatives. Thank you. Today's presentation consists of four company overview of the new supercomputer plasma and also our company profile. And NEC was founded in 1899. NEC has led the transformation of customers and society through the implementation of advanced technologies and practice of DX. And in facial recognition in the technology, a few times we have been recognized as the number one in the world, and we have more than 100,000 employees with diverse human resources. And we would like to be the leader in transforming society. And using HPC adaptation, we'd like to compete against the customers so that we can all contribute in the development of science and technology. And this is the history of NEC computer. 1958, that we started collaboration with Tohoku University, and we started developing high performance of computing systems in 1980s. Vector, we used the SX series. We have been producing SX series. And 2002, the Earth simulator is now became globally known. And since in 2000 and GPU, we have been using GPU and CPU technologies appropriately to realize valuable research. DX and the plasma simulator is the latest product. And now I like to talk about plasma simulator. And the plasma simulator, QST and NINS join forces to implement a system. And this is to calculate complex plasma to accelerate fusion energy. And this is the latest computer. And that the performance reaches 40 petaflops. And this is the world global ranking of supercomputers. November last year, Green 500 was published, and Plasma Simulator ranked first in Japan and 26th or worldwide. And Green 500 is a ranking that evaluates the energy efficiency of supercomputers, ranked by power efficiency calculated by dividing the benchmark performance of the world. So it's a environment-friendly computer. This is the system configuration of overview. There are 3 subsystems, 2 storages, and it is combined as it is described in diagram by combining 3 subsystems. And depending on the application you are using, you can assign appropriate jobs, and this is very good in a way that HPC can do machine learning. System A is a CPU node, and CPU is APU, and the GPU and CPU are combined. System C is called fat memory. It's installed with a very large memory. And I'd like to explain the subsystems one by one. And the subsystem is Intel's that use the Granite Rapid and MRDIMM, the latest components introduced first in Japan compared to previous system. The number of cores and computational performance have improved significantly, enabling large-scale calculation and diverse research needs. And subsystem B is also, this is the first case in Japan, and our greatest feature of this is AMD CPU GPU combined processor MI300A. And this is the first case in Japan that this processor is also adopted by the current world Super One computer and provides cutting-edge computing environment optimized for MI and ML application. And MI300 in the top 500, it's number 1, and it is used in the number 1 supercomputer in the world. And the subsystem C is embedded with fat memory, large memory. And it needs a large capacity memory. And so this is the best if you need a large capacity memory, and it has 16 times more memory. And now I'd like to more talk about what we are doing with regard to plasma simulators. Plasma simulators, we have abundant experience and know-how in this space, and we were able to provide optimized system experience and expertise. And the GPU has been widely used, but it is not easy to utilize GPU and to improve the performance to a max. It's not easy, and it's GPU optimization, application, and the parallel calculation through those analysis. Then to QST and NIFs, we optimize the performance and the latest GPU and memory. There are different configuration and settings, and there are infinite number of parameter combinations. And the optimization is we have the expertise to be able to optimize the configuration. As a result of that, and first application adaptation in Japan, from the get-go, we were able to perform to maximum performance. And the second was that high-speed technology. And GPU itself has a great performance, but hundreds or to using 10,000 of calculation core, the scale performance in that setting is not easy, and there are so many different challenges we faced. And the GPU parallelization, memory layer or hierarchy, we have to understand the architecture to optimize the algorithm, and that requires expertise. That's where we came in, and to QST together with a QST, the code analysis and optimization was something that we were able to provide. As a result of that, we were able to maximize the performance of the system. And going forward to the future, and first, research information infrastructure with the rapid development of AI in research, data is becoming larger and larger and more complex. The research data management and security assurance have become a major theme in the academic research. To address these challenges, we leverage NEC's strengths in high-speed, large-capacity communication and information security technologies to comprehensively provide cutting-edge information infrastructure and support improvement of research capabilities at institute, universities, and companies. And then we are able, and in the HPC and the AI environment, with infrastructure, we can connect these two, and HPC and AI can work together. AI for science is something we would like to support. And in a few years down the road, next generation supercomputer processor, semiconductors for that purpose is something we started development. And OpenTip is the Spanish company, our partner. And Disk5 is the open architecture and vector architecture, which is we are good at. With that, we are going to design new semiconductors. And semiconductor is a national security. In terms of national security, semiconductors are extremely important. We would like to consider how we can contribute. And collaboration with OpenTip company has already been published. In conclusion, NEC plasma simulated through the stable operation of the plasma simulator system, NEC will open new horizons in fusion research and strongly support the realization of a sustainable energy society. This will contribute to the demonstration of scientific and technical feasibility of fusion energy and ultimately to the success of the ITER project, where we will contribute to the dramatic acceleration of research and development through the power of high performance computing and QST. And if I like to take this opportunity to thank you for your collaboration and your guidance. Thank you.
Thank you very much, Mr. Kamiyamane. With this, we would like to close the technical session. Next, we're going to conduct a new initiative in this symposium. That is information exchange between ITER organization staff and students. Let me introduce the participants. ITER staff members are joining us via live broadcast from Japan. Mr. Takayoshi Omae, Deputy Head of Construction Department. Mr. Sono Toshiki, Treaty Implant Section. Ms. Aiko Horie, Budget Planning Section ITER Organization. And Ms. Mio Nakamoto, Magnet Cooling Test Facility Section. From the floor, there are students from Kyushu University Faculty of Engineering Department of Interdisciplinary Engineering, Mr. Naoya Ishibashi, sorry. And Mr. Hayato Hayamaki from Hiroshima University Graduate School of Advanced Science and Engineering, from the same graduate school, Ms. Higashi Nagai. And from a graduate school of Tokyo University, Mr. Haili Jin, graduate school from Science Engineering University of Tsukuba Mathematical and Physical Science Research Group, Mr. Takumi Seto, and Mr. Nakahira Masataka from ITER Project Department of QST will serve as the coordinator. Hello, everyone. This is Nakahira. I will be the moderator. Firstly, the ITER staff will give a brief introduction of themselves, and the students who are now on the stage will give comments and ask questions so that they will be able to have an exchange of opinions and information. From the left, Mr. Omai and Mr. Sono, and Ms. Sono and Ms. Nakamoto. Looking forward for your active participation. So the students, please be seated. Let's start the self-introduction from Mr. Sono about what you do at ITER. Sono-san, the floor is yours. Hello, everyone. My name is Toshiki Sono. I'm a staff at ITER organization. I've been working for 3 years, and I am involved in the treatment plant as a mechanical engineer responsible for mechanical design. And my former job was in a company also in mechanical design, meaning that I moved from the energy industry to the fusion energy. I would like to explain about my job and my life at ITER. Please move on to the next slide. I have been involved in the treatment plant, specifically in mechanical design, and we'll have to use radioactive materials and other hazardous materials, so meaning that safe and reliable plant design is my job. My daily duties include design and analysis of piping and equipment, as well as a creation review of design specification document. The photo shows you the overall treatment plant involving Japan, US, EU, and Korea in charge of the procurement. Therefore, I am in charge of managing the interface of the plant components, which will be delivered from various countries. Moving on to my personal life, there are clearly 4 seasons. A pleasant life in the countryside is what I am enjoying. And I have a wife and daughter in Aix-en-Provence. That is the site where I am living my life. There are some difficulties living in another country, but in the weekend I enjoy trekking around the nature and visiting historical sites. Nice to see you all today. Next, Ms. Horie, can you introduce yourself? My name is Aiko Horie. It's my pleasure to meet you all. I started working at ITER organization in October 2024, so I've been here for a year and 4 months. I am a member of the administration department and a budget and planning service session, and I am in charge of the project control expert. When you hear the name project management, the structure is totally different of what you do and what kind of organization is. Last year, we went through an overhaul of the organization. And so 2 different persons from different department is assigned as the project manager. First is from the construction project office, a person who is called the project lead is in charge of the management. They have been in charge of the management before the restructuring of the organization. Therefore, they're quite knowledgeable of the project. On the other hand, the project control expert at PEC are in a section called Budget Planning Services, which was a derivative of the departments mainly focusing on finance and services. This organization was launched last year. And what I do, in short, is to support the teams so that the project will progress in line with the schedule. And from this year, we have set individual goals so that the schedule will be met. That it was a brief explanation about myself. Next, Ms. Nakamoto, can you introduce yourself? Thank you for your introduction. I am Amio Nakamoto. I joined ITER exactly at the same timing as my colleague sitting next to me. That was meaning that I have been here for a year and 4 months. And my job is Tokamak program and also the Magnet Project Controls Integrated Commission program, specifically Magnet Core Testing Facility program. My job is magnetic engineer, and I am in charge of a toroidal field coil, which is one of the superconducting coils. The photo on the right-hand side is the TF coil. And what my duties are, because all the toroidal coils, field coils are delivered in ITER, we are now starting to start the installation in the pit in the toroidal coil building. So what I'm doing is checking all the coils that have been delivered. The left-hand side photo shows you is the magnetic code facilities subsection, which is the cryostat for the cooling test. So the coils are put into this section so that the test will be conducted. That was with this I like to end my introduction. Now I would like to ask the students to ask questions or give comments so that you'll be able to exchange your opinions. I'd like to, Ishibashi-san, would you like to ask your question first? Thank you very much for giving me this precious opportunity. And my question is related to my desire to work abroad outside of Japan. However, when it comes to my English proficiency and also the limitation and the knowledge and expertise that I have, I am concerned that maybe I am not really eligible in terms of my personal ability. So I want to know what was your case when you made a decision to work over there, and if there's anything that you place importance in working in another country. Are you, do you want to ask this question to all of the ITER members? Yes. So Sano-san, would you like to start? Thank you for your question. Since I was a student, it was my dream to get a job abroad. So I always set my goal working in another country, starting when I was working in energy company. Of course, the language proficiency, expertise in engineering was one of the consideration that I had. However, because I wanted to be a component of diversity by working at ITER, I am trying to convey my opinion and also negotiate with others. These are the important qualities. And even though I'm not saying that I have already acquired that ability, I'm still working on to get those ability. But I think that communication capabilities is important, and I will recommend you to take on the challenge and to make a decision to work overseas. My comment is quite similar to what Sono-san says. English proficiency and ITER, that can be one of the concerns that you have. But honestly, more than half of the ITER staff are not English natives. So both of us try to convey what we think as much as possible, and at the same time try to understand what the other people are saying. So you don't have to be perfect in the English language from the past. You can draw pictures, or you can just confirm by telling the other person how you understood their opinions. So you don't have to worry too much about your English proficiency, and take on the challenge and get a job. In my case, my former job was also working in another country, so I didn't have any concerns about the English language. But as my colleagues have said, even though you're good in English, it doesn't mean that you'll be good in communication. You can use various media to communicate with others in addition to the language. The Japanese who are working at ITER organization right now are working with people from other countries, meaning that there is a system of support already in place in our organization. So please come. Do not hesitate to come. Yamaki-san, would you like to ask questions? I have questions to Mr. Sono. You just explained that you have worked in a private company before ITER. Is there any big difference between Japanese private company and ITER? Someone said in a small voice, money. Of course, the budget size is totally different. And when you say different, everything is different. Private versus public, and also industry-wise, it's totally different, because in my past job, I only dealt with established technologies. However, in the case of ITER, the incubation period have just ended, and it's now about to take flight. And even though I had experience working in another country in my previous job, in terms of diversity, ITER is quite unique. It's not only about nationality. The background is different. Some people engineers, some has a science background, and also some of them are procurement specialists. In this perspective, I think that it is quite unique. Thank you very much. Higashi-san, Mr. Higashi, would you like to ask a question? I am Higashi. Maybe I should say good morning to you who are taking part from France. I have a question to all of you. ITER is such a huge project. In addition to that, you are living in France. That can be a big decision that you had to make from the perspective of your total life. And I think that I will have to make similar decisions going forward. I want to know how you made that big decision, and whether you had any special concerns, and how you have overcome those concerns and made that rigid decision. I would like to hear from all of you. And Nakamoto-san, please start. As I earlier mentioned, working abroad was not something very difficult for me. And at a timing when I was searching for a job, there was this big project drawing attention in Japan. So my decision was, there's no choice but to get this job. In Japan, I think that it's difficult to go to another country and get back to that place once again. But I think should be no negative elements in getting this job. So that's the reason why I made the decision. I worked for more than a decade in Tokyo, and so I was a kind of tired of continuing that job. I wanted to experience life in overseas. France is not that convenient. For example, when I was leaving my house, the gate didn't open. I was wondering whether I will be able to make it to this meeting. But I feel that this kind of difficulties and inconvenience had maybe growth. Maybe you do have concerns worrying about many things, but you'll be able to manage them. So don't worry. Make a decision to come. In my case, it has been a dream to work abroad. So it wasn't difficult. But I am here with my family, a wife and daughter. So it was not the decision that I can make alone. I have to talk about this matter with my family and members. And based on the discussion, I feel lucky because they decided to support me. So maybe going forward, you'll start to have your own family, meaning that you'll have to think of their life in addition to your career. Next, Jin-san, please ask a question. I'm Jin from the University of Tokyo. I have a very technical question. In participating in an international project like ITER, what was the most impressive or the biggest challenge that you have experienced, both in terms of technology and life? For engineers like us, what kind of scientific and technological skills will be necessary in order to get a job at either organization? So I would like all the members to answer that question. Then, Sono-san, would you like to start, please? The biggest challenge for me is the fact that I will have to design everything from scratch because this project is unprecedented. Leaving the details apart, if there's some similar plans somewhere in the world, you can just build on that model in terms of design. But ITER is different because this is the challenge that has taken on by humankind for the first time. We don't find any precedents. We have to think of totally new approaches. I think that this is the biggest challenge that we have to take on at ITER. In terms of the skills that we have to acquire, it's not about technical skills or the technological skills. You need human skills. And this is something that needs to be built up continuously so that you'll be able to have a foundation that you can utilize when communicating with other people. As a project manager, because this is what I do, the skill that I need is communication skills. Even though ITER is the top of the world in terms of the technological aspect, but at the same time, this is a melting pot of the variety of people that you'll never be able to find in the world. And you have to communicate with the variety of people. So you have to make efforts to understand what the other people is trying to communicate, as well as what their roles are. So the skills that I think that is necessary is the communication skills. Nakamoto-san, over to you. What I had difficulty when I came here, maybe this is due to the nature of the job. Manufacturers from India and Italy were mostly my counterparts. Their attitude, their carrying out the job is different. And just like Hori-san mentioned, sometimes the conventional wisdom is not the same depending on the different background. The superconducting course manufacturing at ITER, there are quite strict limitations because there are specific requirements. And when we need a skill to logically analyze where the problem actually lies. I just wanted to say thank you to all of you. And finally, Mr. Seto, can you ask a question? I am Seto from Tsukuba University. Good morning, everyone, and thank you for the opportunity. I want to know about the teamwork in the ITER project, which is just expansive. From the perspective of teamwork, what did you find was a benefit, whereas what was the difficulty? Maybe this overlaps with the previous question. So please, three of you answer that question, starting from Nakamoto-san. Talking about teamwork, we work with people with different specialties, different backgrounds. Even though I'm in charge of superconducting coils, we'll have to have knowledge from different specialties, meaning that we'll have to continue discussions on a continuous basis. That is the basis of teamwork. In my case, I try to talk with my counterpart face to face instead of relying on online communication. We can feel the sense of a unity and the sense of what the other people are feeling by face-to-face communication. So I try to practice this. As touched upon my colleagues, I traveled to France from another country, and that's common with my colleagues because they have come to France from another country, and often not limiting to our job. There are many concerns, difficulties living in France. Sometimes we complain about other country, but this kind of communication is important. By sharing this kind of views, even in our job, we're able to communicate better. Thank you very much. Even though you may want to have a further discussion because of the limitation of time, for the students who have participated in this session and all the members from the ITER organization, please give a big round of applause as our token of gratitude. Thank you very much.
So back to Tokyo. Thank you very much for participating. On behalf of the organizer, I will have Takenaka Hidenobu, the chairman of organizing committee for 2025 annual symposium ITER and BA activities. I'm Hidenobu Takenaga, Deputy Chair of the ITER BA report symposium on ITER and BA. Thank you very much for taking time out of your busy schedule to attend the 2025 annual symposium on ITER and BA. We just heard 359 people attended this symposium, more than those who attended last year. In organizing this symposium, our committee has worked together with representatives from universities and industry to plan a program that everyone would enjoy. So as a first attempt, we had a discussion session between the ITER staff as well as students. I think we put into a lot of content into symposium. Maybe it was too busy, so I'd like to take that lesson to the next symposium. But through the discussion, students and young engineers, I hope that the exchange session will inspire students and those researchers to consider a career at the ITER organization. We will have a closer relationship with the industry so that we can realize the demo reactor and fusion technologies realization as soon as possible. We would like to express our sincere gratitude once again to everyone involved. And I'd like to wish everyone all the happiness and good health. Thank you very much for your attendance today. Thank you very much. Thank you for spending long hours to attend the 2025 annual symposium in ITER and BA activities. With this, I would like to close the symposium. Thank you so much.